Let's conduct a more realistic experiment by heating a rod about where the heat really was in the towers, and see if the top accelerates down by gravity alone. Let's conduct a more realistic experiment by heating a rod about where the heat really was in the towers, and see if the top accelerates down by gravity alone. Obviously, the top doesn't accelerate down by gravity alone, even if I hammer it down. There are some very good simulations, and some really bad simulations because they don't run long enough, and of course they don't match reality.
Which led to a single column, one column that had a large unsupported length, and that one column, the critical column, buckled.
But when asked, how could he be so sure the Building 7 model was accurate?
And to use a very complicated computer model for this, how can you be so sure that this is actually accurate, what you want? It's a virtual proof, some might say.
Well, computer models these days are incredibly robust. We actually design 1,000-foot, 2,000-foot buildings today purely based on computer models. We design airplanes that fly with computer models. We certainly can do failure analysis using computer models.
For example, the building can't sway in the wind or have bouncy floors, even though it may be perfectly strong. Building codes have an allowable deflection, and for the towers, it's the beam length divided by 360, or L over 360. Ideally, any experimental model should meet these two basic requirements. The pancake theory, where gravity drives both the down and out motions, was promoted by FEMA and the American Society of Civil Engineers. PBS showed us a computer model demonstrating how the floors will continually fall down. But is that right? To test this, I used some cement-type planks and a solid block of steel that weighed about 20 pounds. Placing a steel block on the cement board, I measured the deflection for various numbers of planks. The plank span is 19 inches, and the maximum allowable deflection is therefore 19 divided by 360, or 0.053 inches. So the minimum number of planks needed to meet deflection criteria would be 4 planks for that particular design load. I built a tall support structure so I could test the theory, hopefully confirming the PBS model. Dropping the steel block first on the floors that met code deflection yielded a very different result. So I reduced the number of planks which didn't meet deflection criteria, and still the block decelerated and eventually stopped.
Oh, I'm falling. Yeah, I'm falling. Oh, I'm falling.
And then it stops. Using the same cement planks, I made some small floors that could be reused over and over. I had to build a steel guide rail system, otherwise the top section would continuously fall over. I decided to use some weak plastic pizza cover supports as my columns. Dropping about 15% of the floor system on the lower structure always demonstrated a deceleration. I even removed the upper plastic supports to make the falling floors denser. But it still didn't match the observed motion and never experienced the crush-down, crush-up result predicted by the equations. So I decided to make an unrealistic model where the supports were turned sideways and even weaker. The deflection was excessive, and just like the 9/11 Commission, they were set up to fail. Finally, it looked like I was starting to get the motions observed. But when we slow the action down, we can still see that the upper floors always decelerate, and we never see the crush-down, crush-up motions predicted by the pile driver theory.